Okay, guys. I'm doing this notes ad as a video. Sometimes I'll do that, and sometimes I'll just give you the PowerPoint. So here goes. I have to wrap this up in 15 minutes. So if I start talking fast, just pause so you could get the information that you need to get, and then continue writing. You're gonna fill out your note sheet as usual and turn this in on Canvas. All right, here we go. So in this unit, we're gonna study the atom. We're going to investigate the atom. An element is matter with a fixed composition. It's made of the same atoms. An atom is the smallest piece of matter that still has the properties of that element. Important people. So we started off with you guys doing a little bit of research. So everyone should see a little bit of what they researched in this presentation, or at least in this portion. Didn't have anyone do Democritus because he was 400 BC, and I worried that you guys wouldn't be able to find any information about him. But he first suggested the existence of tiny particles that make up matter, and he called them atomos, which means indivisible. Next, we had Dalton, and he's an English scientist from the 1800s. He began the modern process of discovery of the atom. He studied the ratios in which elements combine in chemical reactions and developed a theory to explain his findings. His theory said that matter is composed of extremely small, indivisible particles called atoms. Atoms cannot be subdivided, created, or destroyed. Atoms of the same element are identical, and atoms of different elements are different. He said that atoms with different elements combine in simple whole number ratios to form chemical compounds. In chemical reactions, atoms are combined, separated, or rearranged. So that kind of ties in with what he said before, that you can't create or destroy them. Atomic model. So the model that we have now pretty much evolved over time. So I'm just gonna take you through how it has evolved. So Dalton's atom, he thought the atom was an indivisible sphere, right? He discovered that gases have negatively charged particles using a device called a cathode ray tube. So if you did J.J. Thomson, this should be a part of what you found out. He called the particles that made up the beam electrons, and he discovered that all elements have electrons. In an experiment similar to Thomson's was used to discover particles with a positive charge. Scientists knew that there had to be something that was positive in the atom because an atom is neutral. So if there were negative particles, the electrons, then there must also be positive particles called protons. Thomson's model is, he thought the atom looked like a plum pudding sort of situation. So his model was a plum pudding model. So far we have Dalton's model and we have Thomson's model. Next comes Ernest Rutherford. He was conducting a lot of research with radioactive materials, and he designed an experiment called the gold foil experiment. So again, keywords that you should have if you did this guy. He bombarded gold foil with a positive radioactive particles called alpha particles. His model discovered that atoms were mostly empty space, but had concentrated positively charged space called a nucleus. So now we're moving away from the plum pudding and we're saying, oh, all the positive charges are centered together in one space. Negative electrons were scattered around the outside of the nucleus. So far, so now we've changed, again, we just changed from the plum pudding to Rutherford's idea and how that added to. So again, I want you guys to think back to our checks lab that we did. This is, again, how science works. You think something, you come up with an idea, you learn a little more, you change that idea. And that's precisely what happened with the discovery of the structure of the atom. Next, we have Niels Bohr. He's a Danish physicist from 1913. He proposed a model of the atom in which electrons are in fixed orbits, set paths around the nucleus. Each orbit corresponds to a particular energy level where an electron can exist. So here's a picture of what his model looks like, and we will do a little project and make our Bohr model of some of the elements. So far, here we are. So the modern atomic theory was developed by Louis de Broglie and Edwin Schrödinger. Electrons move in indefinite paths, and their exact location can only be predicted based on their energy level. The modern atomic theory calls its model the wave model, or the quantum mechanical model, which just means electrons move in clouds. The electron cloud model is the area around an atom's nucleus where electrons are found. The electron cloud is much bigger, around 100,000 times bigger than the nucleus. So that's the history. That's what you guys hopefully uncovered in doing the project that you did. All right, so the atom is, again, the smallest particle of an element that retains the properties of that element. There are three main subatomic particles: protons, neutrons, and electrons. You have this table in your notes. I want you to go ahead and fill it out. So the protons, the symbol is E minus 1. The charge is minus 1. The relative mass is 0. It's really, really small and light compared to the others. And it's located outside the nucleus. The proton symbol is P plus 1, or sometimes you just have P plus. Charge is positive 1. Its relative mass is 1, and it's found inside the nucleus. The neutron, NO, the charge is 0. The relative mass is 1, and it is found inside the nucleus. So, distinguishing atoms. The number of protons in the nucleus determines the element. All right, this is the atomic number. So that's that number that's circled there. Right? Since atoms are neutral, the atomic number also tells you the number of electrons. So as long as it's not a charged particle, the number of protons is always going to be equal to the number of electrons. Then we have the mass number, right? The number of protons plus the number of neutrons. There are two particles. These are two particles. These are the two particles that make up the mass of the atom. Because if you remember, the relative weight of the electron is 0. So the protons and neutrons are what make up the weight, the mass of the atom. So the notation, the mass number is usually at the top. The atomic number is usually at the bottom. Sometimes they'll have a key because some periodic tables are just different. They will tell you what is where. So there's always a key to tell you where they're putting it. Protons in this case is the atomic number, which is the number of protons. So that's 8. So the number of electrons should be 8 because it's not charged. If it was charged, you would see a plus or a minus something on there somewhere. All right, and then the number of neutrons is going to be the mass number minus the atomic number. So that's 15 minus 8, and that's going to be equal to 7. All right, so sometimes you will be given bits and pieces of this, and you'll be asked to find whatever part you need to find. All right. This is another notation. Sometimes they'll just write that the name of the element, and they'll just give you the mass number. All right, so if you are not given the atomic number, just look at the periodic table. If you have protons and neutrons, then add them. That gives you the mass number. If you don't have protons and neutrons, take the mass number from the periodic table and round to the nearest whole number. All right, so ways to get the numbers. I want you guys, we'll do this one in class. We'll do this in class as a little challenge. All right. Isotopes are atoms of the same element. They have the same number of protons, but with different numbers of neutrons. They have a different mass number and different masses, obviously. Isotopes behave the same way chemically because they still have the same number of protons and electrons. All right, I don't think you have this table, but this is neon, and these are the isotopes of neon. So you notice that the number of neutrons are different in all, really. All right, atomic mass, the actual masses of protons, neutrons, and electrons are all very, very small. Therefore, we compare the relative masses of atoms, all relative to a reference isotope as a standard. Scientists picked carbon-12 as a reference isotope. Carbon-12 has a standardized mass of 12 AMU, so atomic mass units. Okay. The average atomic mass, this is the weighted average mass of the atoms in a naturally occurring sample of an element. So you have to take isotopes and their relative abundances into account. And we're going to stop there for today, guys. Fill in the note sheet and turn her in.